Here we are to conduct a hypothesis test. It says you are conducting a study to see if the proportion of women over 40 who regularly have mammograms is significantly more than 0.35. You use a significance level of alpha equals 0.02. We're given the null and alternative hypotheses, which is convenient. We don't have to think about that part. You obtain a sample of size n equals 496, in which there are 193 successes. So then we're asked to go forward and find the critical value, the test statistic, the p-value, and make a conclusion about the claim. So in short, we are completing the hypothesis testing process, and we can use the guide to help us with this. Okay, we already have the hypotheses figured out, but we'll go ahead and enter that into our form. So it's a proportions test. That means we're going to be doing a z distribution test using the standard normal distribution for a critical value in our test statistic. Okay, so this would have been a claim that became the alternative hypothesis. I'm assuming that. It's possible it was something else, but we don't. So let's read this again. You are conducting a study to see if the proportion of women over 40 who regularly have mammograms is significantly more. Yes, so the claim is greater than, that's why it became the alternative hypothesis, because there is no equality in that statement. And the hypothesis containing the claim is the alternative, which means that if we reject the null hypothesis, we will have support for the claim. And this is a right-tailed test, and we're using the z distribution because it's a test about a population proportion. All right, then we're ready to start our sketch here. So let's use the drawing over here to get. It's always important to draw a sketch to go with your test. Even if you think you know what's going on, a lot of times if you don't do a sketch, you could miss something important. So go ahead and start sketching it out. It's a right-tailed test, we determined, because the greater than symbol is in the alternative. That means since it's a right-tailed test, your significance level is contained completely on the right. We were told to use a significance level of 0.02. So we're looking for this critical value right here, which would be a positive z-score. And I know it's positive because the z-score in the middle is 0, and this one would be to the right. So that would have to be a positive critical value. And it is a z-score. Again, we know this because whenever we're doing claims about proportions, we always use the standard normal distribution, which has z-scores across the horizontal axis. So using our spreadsheet here, we can do the math, finding our values to label on the sketch. So with an alpha of 0.02, that gives us a z-score that is positive. Now, the area on the left, to the left of this here, is actually this over here. That's what the computer is going to think we're giving to it when we use the norm.inverse function. So this is 0.98 over here. So I can do that left area here, 1 minus the area to the right would give me the area on the left. And the area on the left can be used with norm.inv, the inverse lookup, the left area of 0.98, a mean of 0, and a standard deviation of 1. So that critical value is 2.054, and we can enter that answer in. But before we do, let's go forward and find the other two important values here for our sketch, the test statistic and the p-value. So the test statistic is where we take our sample statistic and turn it into a z-score so that we can compare it with this critical value, because this critical value is our goal post. If we can find that our test statistic is that extreme or even more extreme, then we will reject the null hypothesis. So we need a z-score that we can compare with this. Okay, so the test statistic, I'm going to use green to show it, and it's either going to fall outside of the rejection region or in the rejection region. And that's what we need to know. So we're calculating a z-score using the formula from the formula sheet, and I have copied it here. It's this one with the p hat and the p's in it. So that's my test statistic formula. Now, what do I need in order to calculate this? What are the pieces I need? I need p hat. That's my sample proportion, p hat. I need p. I need q. And I need n. So let's see if we can find all those bits of information in the problem. It says you are conducting a study to see if the proportion of women over 40 is significantly more than 0.35. So remember, that was our null hypothesis value. P equals 0.35. We're assuming that that's true and looking to see if there's evidence against it. So we'll put 0.35 here for our population proportion, and Q is 1 minus P. Whoops. Okay, that cell happens to be protected. I'm going to unprotect this just to make it easier on myself. Use the password unlock. Equals 1 minus this. Okay, so now I have my P and my Q. It said here a sample of 496, so that's my N, my sample size. There were 193 successes. So I can use that, 193 successes divided by the sample size gives me my sample proportion of 0.39. So that sample proportion is what I'm trying to turn into a z-score so I can tell where it is relative to this critical value. So let's convert that to a z-score. So we're going to do z equals the sample proportion minus the population proportion divided by the square root of PQ over N. This is our standard error. So it's the sample proportion minus the population and divided by the standard error. So we have 0.39 as our sample proportion, 0.35 as our population proportion, divided by the square root of P times Q all over N, 496. All right, so I'm going to do that in here. And I'm expecting this to be positive because it's 0.39 is to the right of 0.35. It's greater. Okay, so we have a positive. So it's 0.39 minus 0.35 divided by the square root of 0.35 times 0.65 divided by N, 496. Make sure to close the parentheses so it doesn't yell at you. And then you have 1.868 as your test statistic. You can also set this up if you want it to do automatic calculations for you. You can do your p hat minus your p, close parentheses, divide by the square root of 0.35 times 0.65 divided by 496. So my test statistic of 1.826, that actually fell outside of the rejection region. So I'm going to fail to reject the null hypothesis. So my value here, 1.826, outside of the rejection region, we fail to reject the null hypothesis. Also, that's our test statistic. We can use that to find the area to its right, and that will be our probability value or a p-value. This is the probability that we would get something at least this extreme by chance. So we'll use, how do we find an area in the tail next to a z-score? We use norm.distribution. We need to give it the boundary 1.826. Remember that when we do, and we give it the mean of the standard deviation and say yes for cumulative, okay? Now when I press enter, it's going to give me an area under the bell curve. It's going to give me an area to the left of this boundary. So it's going to give me a much larger area than what I want, because I want the one on the right here, the little tail. Okay, so watch what happens. Here I'm going to press enter. See that? You see how it's so close to 1? Remember, the entire area under the curve is 1. That's way too big. I have to subtract that from 1. 1 minus norm.distribution because it's on the right. If it was to the left, I wouldn't have to subtract from 1, but here I do. So there's my p-value. Okay, let's go ahead and enter these and see how we did. So the critical value to 3 decimal places, 2.054. The test statistic to 3 decimal places, 1.826. And which one is more extreme? Which one is farther away from the center? The critical value is more extreme, right? So the test statistic is less extreme than the critical value. That's what leads us to fail to reject the null hypothesis. What about our p-value? Our p-value to 4 decimal places is 0.0339. And is it smaller than alpha? Is it smaller than the significance level? In other words, what we're asking is this area smaller than this area? Because if this area were smaller, it would mean it was a very rare event, and we would feel like we were doing a good thing by rejecting the null hypothesis. It would be considered a wise decision. But here we have a probability that's much greater. So that would be too great of a probability to risk making a type 1 error, rejecting a true null hypothesis. So long story short is to say that the p-value is not less than or equal to alpha. It's not small. We have this little rhyme. If the p-value is low, the null must go. Well, the p-value here, it's not low. It's not less than alpha. So we will fail to reject the null hypothesis on that. So it is not less, it's greater than alpha, and therefore we fail to reject the null hypothesis. Finally, we can draw a conclusion regarding the claim. And before we start picking a choice, we need to know if we are considering rejecting the claim or if we're considering supporting the claim. And the way you know is if the claim fell into your null hypothesis, then it might get rejected along with the null hypothesis. So notice here that our claim was that the proportion of women over 40 who regularly have mammograms is significantly more than 0.35. So that was a statement. The claim that we were testing was a statement that had no equality in it, and it became our alternative hypothesis. So this alternative hypothesis, in this case, it is our claim. That doesn't happen every single time. Sometimes your claim can be in the null. And if your claim is in the null, it can be thrown out along with the null. But here, our claim is safe, safely tucked away in the alternative hypothesis. So if we had rejected the null hypothesis, then we would have support for the alternative. But we did not reject the null hypothesis. So we have not ruled out the possibility that this is true, therefore we don't have support for the alternative statement. So let's look for the one that says there is not sufficient evidence to support the claim. There is not sufficient evidence to warrant rejection of the claim. Nope, that's not what we're talking about here, because that would be the right choice if the claim fell under the null. But here, it was under the alternative. So the sample data, there's not sufficient sample evidence to support the claim. That's the one we want right there. Okay, and we are done.